All right. So, and here's what happened. It occurred to me as I was starting to review tree stuff that all the, especially like the traversal algorithms to traverse trees, all involve recursion. Every single one of them is a recursive function.
They're having like check the condition of each child.
Well, you just no, because what you're doing is because you're doing a lot of down and back, and kind of like what you're saying, but just by tradition, if nothing else, these algorithms have been developed recursively. Now, does it mean they have to be? Absolutely not. Just remember this: anything that's recursive can be implemented iteratively. In fact, that will probably be one of your homework assignments that I'm going to give you later, is to take the recursive functions that I demonstrate today and rewrite them as an iterative function instead. All right, so it's interesting that you bring that up. Recursive functions, when they are compiled and assembled, get assembled into an iterative solution, because there is no recursion in a low level. Assembly language doesn't have recursion. So the deal is that a lot of times, and I'm not good at this because I'm not a big recursion freak like some people are. There are problems that are best solved through recursion. The solution is found easier recursively than iteratively, but iterative solutions are always faster. But
better memory?
No, just faster, just more efficient. Well, not better memory, but if I need to point y'all to some diagrams of recursive functions, because you will see that recursion does take a lot of memory. Because what happens is, well, let's look at an example. All right, so let's start off with factorial. So we all know what factorial does. So like 4 factorial is 4 times 3 times 2 times 1. Right? And we use factorial in combinatorics to do things like figure out how many ways you can combine things. Okay. So let's look at the iterative solution would be, well, you could do it 2 ways. So let's say you're going to find the factorial of 4. You can either start out and say 1 times 1, then 1 times 2, then 2 times 3, and then 6 times 4 to get 24. Or you could count down and say, and go from 4 to 3 to 2 to 1. You can either go up or down, it doesn't matter. Okay, an iterative solution would probably go up. The recursive solution is going to go down, starting at where we're going to start, with the number we start with, and then go downwards. Now, this is where I hate not having a drawing application. All right, so I'm going to do a notepad here. She missed the aha moment where the idiot instructor realized that what I'm drawing on this smart board is not recording. It's not recording on my computer monitor. So I need to start a
That makes me feel better. Oh, we all have these.
Well, and then as you get as old as me, they become more frequent, to the point where that's all you have are these moments, and it's like, oh my gosh, I need to just go retire to the rocking chair.
Hey, nothing can be as embarrassing as you're in the room.
Oh well, okay, but
How am I really here?
I've also got there's a new version of Notepad that I still haven't figured out. It saves all my old things. It's one big old thing of tabs, and there's got to be a way to stop it. But I'm too lazy to sit down and actually dig into the settings to figure it out. All right. Anyway, so we have 5 factorial. Let's do 4 factorial because it's shorter. So there's 4 factorial. All right. So that's equal to 4 times 3 times 2 times 1. Okay. So a recursive function, so what recursion does, recursion tries to put off the computations until you get to where you're stuck, where you don't have anything to do but do the computations. So what if you were trying to view a trying to view it recursively, 4 factorial would start out 4 times 3 factorial. Then it would be 4 times 3 times 2 factorial, and then 4 times 3 times 2 times 1 factorial, and 1 factorial by definition is 1. So then now you have 4 times 3 times 2 times 1. So let me put that down. 4 times 3 times 2 times 1. Oh, I missed it. And then you simply, and then the way you can think of it is the compiler just unwinds it. Or yeah. So now it's 4 times 3 times 2. And then it's 4 times 6. And then you get 24. Okay. So you see how the recursion grows and then it shrinks.
Oh, like Gaussian distribution.
Well, it's not a normal distribution. I mean, you're right. That's a bell curve turned on its side. But that's not. Don't think of it like that. There's no. Well,
Just a happy accident.
I wouldn't say there's any correlation between how recursion unwinds and the normal distribution. I'm not saying maybe there is. I don't know enough math to be able to say that. But that's the idea, okay? And so it's nice to be able to sometimes the recursive solution is easier to see than the iterative solution, and you're going to see that it's pretty easy to write too. And once you see how to find recursion in things, you can write little shorter programs.
Is it easier to debug or harder?
It's harder to debug, and it's less efficient. And for years, compilers, I mean, nobody would ever even dare, if they were writing an efficient program, would dare to write a recursive program because it would be so slow. But now it's not. Memory's cheap, so you can stick a lot of stuff in memory because that's what's happening right here. All these computations are being stored in memory in what's called, I guess, the run stack. Well, yeah, but I think there's another. I don't know. Some of these compiler terms, since I don't study it all the time, I forget. Anyway, so yeah, but all that's got to be stored, and then dealt with until you get to the final solution. Whereas with an iterative solution, you'd just be going and go. It would be faster, and it would use up less memory. But again, like I always say, now memory is cheap and plentiful, so we waste memory like crazy, and nobody cares anymore. Unlike the old days when I used to have to try to write code in 5K of RAM, and that would be like, oh my gosh. Anyway, all right. So, but no war stories today. Because I need to leave early, so I can finish my work. All right. So that's the thing. So let's look at how we would write that code to perform a factorial function or to do a factorial function recursively. So what we always have is there's always 2 parts. What's called the base case and then the recursive step. Those aren't technical terms. Those are Macmillan's terms. Okay, well, base case is. All right. So the base case always is used to figure out how to stop the recursion. So remember that we're doing factorial, so we're doing 5 times 4 times 3 times 2 times 1. Our parameter n is going to be the number that we're trying to compute. So our base case is if n is equal to 1, return n. Okay. Else, return n times, whoops, oh, phone's on. take that out of my salary.
Oh, that's not what I was thinking. That's not what I was
I'm just playing with you. Okay, so there it is. That's the whole, whoops, I didn't put it in the right place. That's the whole definition. Control C, Control V. No, what? Control C, Control V. Whoa. All right, I'll just write it out. It isn't. It's doing some things right, but it's not doing anything right. All right. So you see how it works. So the recursive step is exactly what I showed you in Notepad. Ooh. That worked out perfect. Okay. And so you're like recursion like postpones the computation until you're all the way at the end of your recursion, and then it's got to go back and fill all that in. So that's it's the expand then contract model. Now, I meant to say this at the beginning. There's lots of what are called functional programming languages where this is the only way to loop.
Really?
Yeah. There are no, at least not in the pure languages. Now, most of them have added iterative steps because programmers got so frustrated with constantly having to write recursive functions to do the simplest things. But a pure functional language would have no way to loop other than recurse. So I'm going to probably give you some problems that aren't naturally recursive in nature, and have you write them recursively just for the practice and to see
So
how
like
it is.
running the loop.
Well, like how to print an array. You know how to print an array with using an index for loop, right? From 0 to the size of the array minus 1.
So instead of using a for loop to do it,
It's going to look exactly like that. Yeah. Yes. It's also going to be recorded that I'll post in Blackboard also. Anyway, but let's forget about that for a minute. Okay, so let's test how well it works. So 4 factorial equals fact 4.
is that an exclamation point?
Oh yeah. That indicates factorial. I'm sorry. I thought I saw it. That's in my notes too. Yeah. You didn't know it. I just assumed. So you haven't had discrete math yet, have you? No. Okay. Discrete math. When you've had discrete math, then you will know all too well the fact, because that's when you'll start doing permutations and combinations, and you'll start learning all these formulas for figuring out how many ways you can do things with and without replacement, blah, 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 blah.
I just read the huge math section on 73 schools.
Well, and my advice, if you haven't had it yet, pay much more attention to discrete math than you have been to calculus. If you want for the furtherment of your programming career. Well, and that's just an old. There's really no reason that you should take anything more than calculus 1, if even that. If you're just trying to prepare for programming. Because programming is all about discrete math. It's none about, continuous, trying to find, integrals and limits and differentiation and all that stuff. It's not about, programming is not at all about that unless you're working in physics and engineering. Then you got to know how to do it. But I mean, again, the math that is involved in computer science is all discrete. It will not do you one bit of good for programming. Well, I mean, to be honest, to me, it's more of a let's see who we can cull out of here by flunking them out of calculus a couple of semesters more than anything else. Yeah. So anyway, yeah, this factorials are something you'll use in discrete math all the time. All right, so that's how it works. So you notice that all a recursive function does is it calls itself. That's the definition of a recursive function. A function that calls itself in the function body. Most of the functions that we look at, in fact, the few that we're not going to look at that many today, but the ones we do are all the recursive step is always at the end. Okay. But it could be in other places in the function, just depending on what you're trying to write. But the three that I'm going to show you are going to all be like that. All right. So, again, here's what you have to have. You have to have two things. You have to have a condition that will cause the function to stop. Okay? Just like in a for or while, well, like a while loop especially. Well, any loop. You got to have a condition to make the loop stop, right? For n I equals 0, I less than size of the vector. Okay, vector dot size or whatever it is. Okay, or whatever your thing is. There's always a condition. You've got to have that. And that's called the base case. All right. Then, because it's a recursive function, there's going to be a recursive call. But in that call, you're going to modify at least one of the parameters so that it will affect the base case. So when we call fact4, we're calling fact4, then fact3, then fact2, then fact1, and boom. When n gets to 1, that's when we stop. And that's when that recursion it's unwound, then it gets wound back up or condensed, I guess is a better way to put it. And the solution is computed. Okay. So you gotta have this condition, and you gotta have some sort of modification in the parameter usually to make that go away. Now I'm going to show you one example of a non-recursive function. We're going to print the print array example that I just talked about. And then you're going to, it's the same thing, but it's a little more contrived than natural. I mean, because this is natural, because, right, remember we talked about it. If you look up the formal definition of factorial, it's going to say 4 factorial is equal to 4 times 3 factorial, which is equal to 4 times 3 times 2 factorial, all the way down to there. Okay. All right. Questions? All right, let's hear the joke. Yeah, you're a base case. That's good. All right, let's do another one. Let's do computing of power, because that's another example of it's like my root beer float joke, I guess. You know the root beer float joke? All right, they do, but I'm going to tell it to you anyway. All right, I try to tell this in every computer science 1 class, and I missed it this semester, and I had to go back and tell them later. It wasn't as funny. All right, a programmer walks in and says, I want 2.25 root beers. And the bartender says, oh, that's a root beer float. And the programmer says, in that case, make it a double. Yep. It's hard to find a joke about data types. A string, a char, and a bool walk into a bar. All right, so power. All right, so think about how you compute the power of a number, right? 2 to the 4th power. Right. Okay. And or yeah, so you're just so it's this just you're multiplying that same number x number of times depending on what the exponent is. Okay, so the solution looks almost exactly like what we did for factorial. We're going to count down the exponent. And when the exponent gets to 1, because any number to the 1st power is itself, right? Then we're going to return the base. Otherwise, else, oh, we don't even have to do an else. I did it a little different. So we're going to say, so 2 to the 4th is equal to 2 times 2 to the 3rd. And then 2 times 2 times 2 to the 2nd. Then 2 times 2 times 2 to the 1st. So that's 2 times 2 times 2 times 2, like Tim said. And that's 4. So let's test it. 2 to the 4th. Wish it was easy to write subscripts and superscripts in Word, but it's not. No. There's not a symbol in C++. There's not the caret. There's not a caret. No.
Oh, you mean this?
Yeah, the caret. So that used to be. I mean, in some languages, 2 caret 3 would be 2 to the 3rd.
Yeah, that's how it is.
I guess the caret meaning raise that number up superscripted. Yeah.
So what you're saying is you can't use the caret on your keyboard in the program.
Right. It would. Yeah. It won't work. I have seen that. That goes into D minus minus. I have seen students pull that off, or think they're pulling it off. They put it in their code because obviously they weren't even trying to compile it to run it. They just put it in there and thought, okay, that's how you do it.
They don't run their code before they.
Oh, I can't.
What was the story you told us last week?
Which one?
The one about the guy that didn't run his code, but what was it?
Yeah, he submitted Python. So what's happening is students are using ChatGPT to do their homework. And so if you don't specify the language to ChatGPT, it spits out Python by default. So this summer in my C++ class, I had them doing, so I don't remember what it was. Maybe probably arithmetic because it was early in the semester. And the code I got back was Python. And so I started to put in the feedback. You're getting this class confused, but then I hadn't typed it all in. Well, wait a minute. That's not what happened. They used ChatGPT and just didn't even bother to look to see what the frickin' program returned. Oh, I was mad. That's the maddest I've been in a long time over something like that. Well, all right, until today. Until today. Today I got an email. I woke up to an email from a student in my computer science 1 class asking me, and I've been given the same test, and not the same test, but the same format. Half in class, half take home. And I say it over and over again. I tell them that the first day, I say it before the test, I say it the day of the test while they're taking the test. Thursday was their test. No, Tuesday was their test. Thursday they had to turn in the take home part. I get an email this morning from a student saying, oh, was I supposed to do the in-class and the take home? First time that's ever happened in years.
You say, well, what did you
No, I just said yes. I'm going to have to take a few points off because it's so late, but yeah, go ahead and do it and turn it in. I try not to be that instructor. All right, so 2 to the 4th is 16. So again, it's probably a lot faster to write this code iteratively. In fact, I usually assign that as one of the function problems to write, is rewrite the PAL function with a loop. That's a good looping problem. And it's easy. Yeah.
It's also just
Oh, I know. All right. So the two guys who created Unix, and the guy who was primarily responsible for creating C. All right. So Ken Thompson was the guy who was mostly responsible for Unix back in the 68, 69. So before that, there are all these big, huge, these big, mainframe operating systems, and none of them worked very well, and nobody liked them. So Ken Thompson and this guy named Dennis Ritchie came up with Unix, and at the same time, I tell this all the time. They wanted a high-level language to write Unix in, so they invented C, which came from the language B, which was another language that was around before that. Okay. Well, Dennis Ritchie, who was the primary developer of C, at the same time that he was working with Ken Thompson, they both worked at Bell Labs. They were kind of like partners. He had just finished up his PhD in mathematics at Harvard, and his area of study was recursive function theory. But he has said that after studying that recursive functions mathematically, and then he started working on programming languages, he has said many times that he prefers iterative languages over functional recursive languages. Right, you break it down, then you build it back up again.
That is how we do it, but that's not what we want the computer to do. We want the computer to just.
Right, and so his point is that iterative solutions are always more effective than recursive solutions, and you're not going to sit around and implement an operating system, especially back then when processors were so slow, using recursive techniques. But anyway, it's kind of an aside. All right, so let's look at, there's two very common and classic examples of recursive functions. And again, you can, it would be almost a mechanical process to rewrite those with a loop, especially since you've probably done it for most of these already. I probably assigned it at some point. All right, let's look at a problem that's not recursive, but that can have a recursive solution. All right. So I'm going to create a simple little array. And so we would write a little, so let's write a function. Let's write an iterative function to do that first. We'll call it void iter print.
His response was basically, thanks, I hate it.
Have you ever seen Hipster Ipsum? Google that sometime. It's just all hipster words instead of Latin. Instead of Latin. It's just yeah.
I was like, no, I memed on him for a semester and I got an A. How dare you?
All right, so here's the iterative solution. A simple for loop that we start at 0, we go through n, well, less than n, increment I by 1, write out each element of the array. You can do it in your sleep. All right. But you can do it recursively. Where is it? Here it is. But it's a little more involved. So our base case is going to be I equal to the size of the array. I is going to be another the variable that we use to index into the array. And if I is equal to n, that means we've gone past the n, so we're going to stop, and just to mark the end, I'm going to put a new line. Okay. Otherwise, I'm going to write out, and you'll see, first you're going to look at this and say, how does that work? Because I doesn't get a value, but of course I is going to get a value when we call the function. Otherwise, we're going to write out the array sub I, increment I to the next element, and then call the function again with the array name, n for the size of the array, and I. So that's how so here, in our other recursive examples, we were decreasing the parameter by 1, the exponent or the number in factorial. But here, since we're going from 0 up to the last element of an array, we're going to increase I. And then to call the array, so we'll just comment out my iterative function. And we'll call print array with nums 5, 0. Okay. And so that should get the same result. 1, 2, 3, 4, 5. Oh! Ah, that worked. That worked in practice. Hang on. What did I do wrong? It did work? Well, because he's running Visual Studio or and I'm running Code Blocks. All right, all right, hang on. I ran this upstairs. It's the very same code. I must have done something wrong. No, increment I by 1, call I, n, I. Yeah, nums 5.
Oh, nice. Is that the magic movie?
That's what's on the screen.
The only thing I've done different is I made my function a template.
Congratulations, you figured out how to put that. Is that on the background of your computer?
No, what that looks like is every single in every movie when they're displaying someone programming. I always tell my wife, it's like, that's just a infinite loop running a print screen of a program over and over again. Nobody ever does that. No programmer is going to sit there and watch their code scrolling over and over again.
I was going to say, all you need to do is put that on the background and be like, I'm in.
Which I don't understand why someone hasn't.
Those commercials from school, like, come to our
Oh,
school.
so it did do it.
It did.
And then it just kept on going.
Oh, yeah.
I don't know why yours keeps on going. It has the same.
Is it because you have the other one still up and you didn't?
Aside from me making mine a template.
Is it because you still have the iterative one?
No, because I'm not calling the iterative version. I go in, cout in, else. Oh, you use an else.
I do use an else.
Okay. And maybe I should have, or maybe I did. No, I didn't. But that might have been. All right, so it shouldn't matter. Whoops. But maybe it does. Well, no, because I'll be honest, I might have just, when I was writing it out, I might not have done that. Yeah. All right. So, even though I didn't use else here, all right. So let's for fun, let's rewrite that with an else. What's that? That's power. Power. Yeah. Okay. It's gonna work, and I'm really shocked that. Okay. All right. This is probably the way you should write it with an else, instead of it going into that. I don't know that if I changed it after I ran it, I was actually doing two things at once. But again, at my age, I should never. I'm not paying attention enough to either one of them. I mean, well, think about it. If that's false, then it's just going to jump out anyway to the next code, And even there's not another, it's not an else if, it's just an else, so it ought to run. You know, I would never write that kind of code in like computer science 1. Because again, I try to teach them, you got an if, you got an else. You need to branch it right. And I don't want to confuse them with the fact that, well, you know, the else is really kind of, you know, unnecessary since it's going to do that code anyway if it's just a simple if else. But why is it not? Okay. Well, I have to figure that out at some point. Take your else out. Well, because we have found that there's some things in code blocks that don't run, that should run, that run perfectly fine in Visual Studio. Like I said, one of these years I'm gonna get enough energy up to install Visual Studio Code and run it. But it does keep going.
Yeah, instead of being like 700 lines of code, it's like 15. But yeah.
And I have to assume that's trying to access past the end of the array. But you don't know that for sure. But that's the only thing that's getting printed is the array sub I called. So I mean, you have to assume that that's what it's doing. It's going beyond the end of the array. I don't know. So I didn't bring a pen, but I'll keep that right. All right. So that's really all I wanted to do today was remind you about recursion because we're going to hit it. Oh, what do you want to do? We're going to be using it with trees, especially our traversals of like depth first and breadth first and all that stuff. So I didn't want to go into that without having gone back over just the basics of recursion. But these are all I was looking at the algorithms before class, and they're all mostly similar. I don't think they're any more complicated than this. I hope. But if they are, we can deal with it. So between now and Wednesday, I'm still not used to having a Monday, Wednesday class. I keep wanting to say Thursday. I'll give you some little problems to work with recursion. And then I'll also put some reading stuff on trees so y'all can get started reading about trees. Well, if you can just look in Blackboard and see everything that we've done. Are you in Blackboard yet? But it actually said it may take a while to get you into everything. Okay.
I'm gonna have to hunt down Raymond to get here and be like, hey,
He's already gone today.
What?
He's already gone today.
I'm in 2 of his courses that I don't need because I already took them. Like I took programming 2. I already took relational.
Right. Yeah.
From him, and I don't know why he hasn't clocked that. I was already in there. I don't know what he wants to do because you can confirm. I passed that class.
Yeah, I know.
I think I aced that class. I don't.
Yeah, I don't know what I like I said. My conversation was with April and Ashley about this class, so I don't know what's going. I don't know. He and I haven't talked about what's going on with you in his classes.